So I'm going to start. In the last class, we were looking at problems of equilibrium and free body diagrams of cases planar or 2D geometry. So we looked at the various type of supports and the type of forces or moments they provide. Now, one thing which was pointed out to me at the end of the lecture, and possibly I may not have expressed very well, if we have a roller support and we are drawing the free body diagram of AB. Now, here AB could also be at an incline. So, this is the roller support. This is A, this is B. Now, when I draw the free body diagram of AB, I will first show AB. Now, if I try to move the body along the direction which I am showing as X, the body will move. So therefore, no force will be exerted in the X direction, which is parallel to X, reaction is equal to 0. And the force which this will exert will be in a direction perpendicular to X, and this is what we will call as R. This force may or may not be along AB. It will be along AB only under some specific cases, but in general, if we have an incline, if there are rollers like this, then in the direction perpendicular, so the reaction force is not equal to 0 in the direction perpendicular to the possible movement of the rollers. Think of these rollers as a frictionless body. So that means there will be no frictional force which will come on the this thing. Has any feedback come? Okay, it's clear. Okay. So now, having seen this, let us now come to the equations of equilibrium. We've seen how to draw the free body diagram. Now, our equations of equilibrium for a general case, we'll say sum of F is equal to 0 and sum of moments about any point O is equal to 0. So we get two vector equations. Now, in a general three-dimensional case, this implies three scalar equations. Which are these? Sum of forces in the x direction is equal to 0. If we want to obtain three independent equations, we will take sum of fx is equal to 0, fy is equal to 0, sum of fz is equal to 0, and xyz can be chosen at will depending on the type of problem we have. Sometimes when we have incline, we choose x along the incline, or we may choose x along horizontal, it's up to us. But generally, we choose xyz as mutually perpendicular. Even if they are not mutually perpendicular, each of these equations would still be valid. But if we want to get independent equations, best thing is to take three mutually perpendicular directions. And sum of moments is equal to 0. This will also, for a three-dimensional case, lead to three equations. There will be an I component, there will be a J component, there will be a K component. So totally we will get 6 scalar equations for a three-dimensional case. Now, one of the things which is often asked is that student A takes moments about O is equal to 0. Student B takes moments about a point P is equal to 0. Student C takes moments about Q is equal to 0. We can take moments is equal to 0 about an infinite number of points. So does this mean that we will get that means it looks like we will be able to get, we can generate as many equations as we like. And the answer to this is you may be able to get these equations, but the equations will not be independent. We can only get a maximum of 6 independent equations from the equations of equilibrium. And this we can clearly see if we have moment about O is equal to 0. Moments about P will be equal to moments about O plus sigma I times PO cross Fi. If moments about O you take it as 0, now somebody else takes moments about P is equal to 0. As we have shown in the equivalent force systems, moments about point P is equal to moments about point O plus sum of the moments of all the forces about the point P. Now here PO does not contain any I. So this can be pulled outside the summation. So this will give us moments about P and this was already 0 and sigma Fi is equal to 0 from equations of equilibrium. So moments about P is equal to 0 does not give any new equation. It just says two quantities which are already 0, their sum is also 0. So therefore taking moments about new points may not help. But what you will see is taking moments about different points may help you in solving the problem in an easy way. Now, as far as my series of lectures goes, while I have discussed the 3D case, I will be focusing only on the 2D case. So let us look at what are the equations for a two-dimensional case or for a planar case. So in a planar case, our equations are this is first scalar equation along the y direction You sum up all the forces, that gives you the second equation, and the third equation we will get is sum of moments about O is equal to 0, and we write it as a scalar equation because this is a planar case, so moments are going to come only about the z-axis. So when I say sigma mo is equal to 0, for a planar case I am assuming we are only taking moments about the z-axis. So these three independent equations we will get for a planar case. So now let's start with a very simple example. Let's say we have a beam like this. This is on rollers at end A. It is on a pin. It is just on a support at end B. And I'm taking the simplest case. A force, let's say P, is applied at a distance L1, and the total length of the beam is L. We want to find the reactions at the supports A and B. Simple problem, maybe many of you know how to solve it. Let's first draw the free body diagram of AB. So I draw AB. Now what happens at point A? Because we have roller supports, the reaction at A can only be vertical. So therefore, at A, I have a vertical reaction AY. Let me draw this on a new page so that things are very clear. This is AB. At A, I have a reaction AY. What will happen at point B? At point B, it's a normal support, there are no rollers. So in general, what I will get is at B, I will get BY and BX. Notice I can show the unknown supports in any sense of X or Y. Then what are the other forces acting? There's a force P acting at a distance L1. So this is what are the total, this is the free body diagram, assuming the weight of AB is negligible. If weight of AB is negligible, then this will be the free body diagram. Otherwise, if AB weight is not negligible, we have to show weight acting at its center of gravity. And in this case, in the case if AB is uniform, then it will act at the center. We assume in problems like this, if the weight of the beam is not given, we assume it to be massless. So now to solve this, when I put sigma Fx is equal to 0, the only x force in this free body diagram is coming from Bx. So I get Bx is equal to 0. I put sigma Fy is equal to 0. So I will get Ay plus By minus P is equal to 0. So this gives me Ay plus By is equal to P. And the third equation I will get by taking moments. Let me take moments about A is equal to 0. When I take moments about A, force Ay, the moment due to that is 0. The moment due to P, this force will be equal to P times L1. That means I'm now taking the clockwise direction as positive. I can take the counterclockwise direction as positive also. How do I get that the moment is clockwise? R cross F. So I go from A to P. A to P is this direction. And then I take my fingers, I cross them in the direction of P. So I move it downwards and I get my thumb going in. That means, so the force creates a clockwise effect. So this is the moment due to P. Now the Bx will not cause any moment about A because it passes through A. The other force which causes a moment is By, and I will get, now By times L is the moment about point A, and that acts in the counterclockwise direction. So therefore I get minus By times L is equal to 0, and this gives me the value of By. By is equal to P times L1 upon L. So this is how I get By. Once I know By, I can get Ay. Now, this is the full problem. Suppose the problem only asks me to find Ay or the support at A. Then I have to also apply my mind other than the equations. I realize that two unknown forces are acting at point B. So if I take a moment about point B, I will directly get Ay in one equation. I don't need the force equations. I just need to take moments about B. So these sort of things you can use when you need to solve problems. So instead of taking Fy is equal to 0, if I take moments about A is equal to 0 and follow it up by moments about B is equal to 0, I can get the same solutions or same answers. But the three independent equations will be only these three. When I take moment about B is equal to 0, the same equation can be formed from these three equations. No new equation will come. So this is the simplest example. If we want to make it slightly more complex, then what we can do is add some more things here, make this problem slightly more complex. If so, to make it more complex, what I can do, I have AB here. I put the force at an angle. So now what will happen? If the force is acting at an angle, then the same problem, but now the force P is acting at an angle. So we have AY here, we have BY, we have BX. Now what we realize is the force P is actually P cos theta in the minus J direction, and it is P sin theta in this direction. Now this resolution all of you should understand, that if the force makes an angle theta, then with a particular direction, cosine of that component will come in that direction. So P cos theta is the vertical force, P sin theta is the horizontal force. It is not that always cos theta is x and sin theta is y. It depends on how you choose your theta. Here I have chosen theta with the y axis, not with the x axis. So once I have this, then I will get Bx is the force in the plus x direction minus P sin theta is equal to 0. This will give me Bx is equal to P sin theta. Then I will have Ay plus By minus P cos theta is equal to 0. And when I take moments about A, now what we realize is when you take moments, the y component, so this force P cos theta is effectively acting at this point, and so it's acting at actually not this point, at this point where it is intersecting. This is P cos theta, this is P sin theta. Now P sin theta will not contribute to the moments about point A. We only have a contribution from P cos theta, so we will get P cos theta multiplied by L1 minus By multiplied by L is equal to 0, and this is the direction in which we have taken the moments, and so this will give us the value of By, and then we can get the value of Ay. So this is how we work out this problem. Okay, a very simple problem. Next, let us try to do something more involved. So this is now problem 4.1 from the book. Again, quite straightforward. So here what we have is I'm drawing a blown up picture of the end A. Actually it is much small, so there is a curve here, a smooth circle touching the wall. This is the wall and this is point A, this is point B. A and B are connected by a straight line, and then there is a crane like this. So on, and at the point B we have a weight hanging from a pulley, where W is equal to 2400 kg. The center of mass of this crane is at a distance of what's given in the problem. This is 2 meters and this distance is 4 meters. So obviously my figure is not to scale, and this distance is 1.5 meters. I could have drawn a figure to scale, but actually it doesn't matter. So a fixed crane, the problem says a fixed crane of mass 1000 kg is used to lift a 2400 kg crate. If it is held in place by a pin at A and smooth rocker at B, hold the crane. So the crane is held in place by a pin and a rocker at A and B. So this point is B, the top point is A. And it says find the reactions at A and B. The problem is to find reactions at A and B. So this is our original problem. We have a crane with a weight hanging. And so how do we solve this? Now, because we have to find the reactions at A and B, we have to draw the free body diagram of the crane. So let's first draw a picture of the crane. Whatever it is, it doesn't matter. It has some things like this. These details don't matter. We have to be careful about what is happening at A and B. And at this end, from a pulley, a weight is being pulled. So what we do is, wherever the supports are there, we have to cut the supports. So we have cut the support at A, we have cut the support at B, and what we will do is, we will also cut the wire which is holding the weight. So that means if I look at the weight and if you look at the wire, this is the wire with the weight, and in the wire if there is a tension T which is holding, what we get is this tension T in the wire is equal to the weight. And because we are cutting the wire here by an equal and opposite reaction, the tension in the wire which is T here, which is equal to W. So this is what is coming at this end. We remove the weight, instead of the weight we put the tension in the wire because we are cutting the wire. Now what happens at point A? At point A there is a pin. If there is a pin at point A, then what I will get here will be AX and AY. I will have two forces, AX and AY. At B, what do I have? At B, there is a smooth rocker. So if the body moves along the y-axis, it will be allowed to move because there is no friction. So at B, I get a single force Bx. So, and also I have to keep in mind weight of the crane acts from its center of mass. So this is the free body diagram of the crane. Now let's count how many unknowns do we have. This weight W, what is this weight W? This is equal to the weight due to 2400 kg. So in newtons it will become 2400 into G, which is 9.81 newtons. This weight is 1000 kgs. So this will be 1000 into 9.81 newtons. So this force is known, this force is known. We are left with 3 unknowns and 3 equations we know we will be able to get. So therefore, we will be able to solve this problem. If I actually solve this, this distance is 1.5, this distance is 2, and this total distance was 4. So now, when I have to solve this problem, let's do it the way I would do it if it was an examination. So I have 3 unknowns, Ax, Ay, and Bx. The first thing which I will do is let me take moments about A is equal to 0. Why do I do this? When I take moments about A is equal to 0, I will directly get the force Bx. So let's get it. The moment due to the weight of the crane. So let's take moments about point A. Any force for purposes of this can be shifted along action. This is a vertical force, so we need to know the horizontal distance from A to W crane. What is the horizontal distance? It is 2 meters. So I go R cross F. It is in clockwise direction, so I will get 1000 into 9.81 into 2. So that means I'm taking my moments in this direction. And I have this force. What is the moment due to this force? It is equal to the force 2400 into 9.81. So again, the distance is 4. So I multiplied by 4. R cross F, it is in the same direction. Now what about the moments due to B? I go from A to B. That means I'm going down. And Bx is shown like this. So when I take R cross F, I'm going A to B is in this direction. When I take a cross product with B, I'm turning my fingers in an anti-clockwise direction. So I will get minus Bx multiplied by 1.5 is equal to 0. Is this point clear to everyone? Things like this you will have to do in solving problems of planar nature, and there you will be able to take moments by just taking a vertical and a horizontal component of the force and taking their if it's a vertical component of the force, you have to take the horizontal distance. If it's a horizontal component of the force, you have to take the vertical distance and get the right sense from R cross F. You move to the point where the force is being applied, so that is R, and then you turn your fingers towards the force in the direction of the force. If the fingers curl in a clockwise direction, the moment is clockwise. If they turn in the counterclockwise direction, the moment is counterclockwise. So you work this out. If you work this, as I have written in this equation, Bx will turn out to be equal to 107.1 kilonewtons. So this is, and I'm not writing it. If there is something with a plus sign, you get plus. And what does this mean? The plus sign means that the force indeed is in the same direction in which you have shown. So now to find reactions at A, we can either take moments about B, or we can do sigma fx is equal to 0. So once I do sigma fx is equal to 0, the only x components I have here are Ax and Bx. There is nothing else. So when I do this, I get AX plus BX is equal to 0, and this gives me AX is equal to, what is the meaning of minus sign? That AX, which is acting on the crane, is actually acting in the opposite direction to what we have shown. And to find AY, we can apply sigma Fy is equal to 0. That will give me AY minus W crane minus T is equal to 0. And this gives the final answer as AY is equal to, you add up the two weights and that will give you AY. So this is how we solve a problem of this type. So planar problems can be solved by applying some forces equal to, sum of forces is equal to 0, sum of moments is equal to 0. Let me take another example, but in this case I will now go a bit fast. It's also slightly complex. The main crux here is drawing the free body diagram. Possibly I will not even talk of the equations. So what we have here is a structure which consists of, so this is a single structure which is like a T-shaped type of thing where we have, and this is fixed in the ground. Now what we have is, there's a point B here which is tied to a string, and the string is going down and is connected to the ground. Okay, so now this point is A, this point is B. There are two more points here. This point is C, this point is D, this is E, this is F. I'm keeping the same notation because this is sample problem 4.4 from the text. So I don't want the letters to be different in case you study this at home. And what is given is, at A we have a force, at B there is a force, and then we have a force acting here. Four forces are acting here. So these are 20 kilonewtons each. All the four forces are 20 kilonewtons, and each of these is at a distance of 1.8 meter distance between successive So from here we come to 1.8 meters, this force is applied, another 1.8 meters, the second force is applied, and so on. And here it says this frame supports parts of roof of a building, and tension in the cable is given. It is given that in this cable is 150 kilonewtons. And what we have to find is, find the reactions at the ND. We have to find the reactions at the point where this is connecting to the ground. Okay. Now, in any of these problems, again, the first step will be to draw the free body diagram. Now, when we have a string which is connecting like this, the question which often confuses us is, where do we cut the string? And the answer to that will lie as to what do you want to find? Do you want to find force at a particular point? What is your aim of the solution? Now here we have to do an overall analysis of this body. So now what we will do is, the best thing to do in this would be cut the string somewhere along DF, and we will cut the string at DF very close to the point F. So we draw the free body diagram of the full structure. So when I draw the free body diagram of the full structure, let me first show this structure. This is point B, point C, point E, and then I have the string which is going on, and the string is there, and I cut the string very close to F. So now if I look at it, which are the two places, or which are the places in this where I am cutting away some supports, where I am removing the surroundings? The surroundings are being removed at point T and at point F. So now at point F, what am I cutting? I am cutting a string. So what will come in the free body diagram as the effect of F? It will be just a single force shown by T along the direction of the string. And now it will become very clear why I was saying we cut it as close to F as possible. Or we could have cut it as close to D. We cut it as close to F so that when we take moments about T, we will only get one component of the force. Now, the other catch in this, what will come at point E? And this is where a lot of you are bound to make mistakes. We realize at E, we have a fixed support. A fixed support is different from a pin. So therefore, when I draw the free body diagram at E, I will get a force Ex, I will get a force Ey, and in addition to that, I will also get a moment which I will call M at E. And I can show any direction I have taken counterclockwise direction of this moment. Now, these are the forces which I have shown so far in the free body diagram, which are coming from the support. Now, what other forces will come? We have a force of 20 kilonewtons here. We have another force of 20. We have a third force of 20. We have a fourth force of 20. All these forces are there. Is there anything else? The weights are not given, so we assume the mass of the structure is very small. It can be neglected as compared to these forces. Otherwise, the weight would have come. So now these are the forces which come in the free body diagram. Now, some of you could say, why is the tension not coming at the point B? This was point B. Now, the reason why I don't show a tension at point B is because I've continued the same string. I have assumed the string is a part of my system. I'm cutting the string from the ground only at the point F. So therefore, I get only a single tension. Now, it is possible because our structure was A, B, C, D, E. So some student can also solve the problem and can cut the string at this point, but then they'll also cut the string. So you cut out the string here at this point, but from here, this string is no longer there, but on this, we have a string here. So what we will have is that if you cut it here, then what you're doing is this string. So you're cutting the string here, this string, which is at the top, still a part of your system. You've cut the string here, you'll get a tension here. So let me be more clear. You're cutting, if you decide not to cut the string at this point, you make a cut here, you make a cut here. Then only you can isolate the frame. Then what you will get is, at this point B, you will get a tension here. And when you cut the string at this point, the same tension is going to come here, and at this point the tension will come here. These two will cancel out, and this tension is the same as this tension. So you will in effect get the same thing. So therefore you have to be very careful in things like this as to where you make your cuts. So this is the free body diagram of the entire structure. Now if we assume that this angle theta is given to us, which would be given, all these lengths are given to us, length EF is given, the height ED is given, then we will just use three equations. We will use sigma fx is equal to 0, sigma fy is equal to 0, and sum of moments about E is equal to 0 to get our answer. When I do sigma fx is equal to 0, what do I get? This is t, so I will get t sine theta plus ex is equal to 0. So this is what gives me Ex. I've taken all the forces in the x direction. This is the free body diagram. When I do sigma Fy is equal to 0, I will get minus 20, minus 20, minus 20, minus 20. These I get. Then I get plus Ey minus t cos theta is equal to 0. So let me write this again. I'll copy it from here. Minus 20, minus 20, minus 20, minus 20, plus Ey and this will give me the value of Ey. Now for moments, if I take moments about E is equal to 0, that is the part which is new in this problem. So what do I have to do? I have to take moments due to all these forces. So I have to take the moment due to the 420 kilonewton forces. Let's see this. If I'm at this point E, the moment due to each of these is counterclockwise. So I will get, this is 7.2, that's the moment due to this. Then in this free body diagram, Ex and Ey, they will not contribute to moments about E. Moments about E will come, so I will get plus M sub E. Now, if I'm, and this is where the point comes that I've taken T to be acting at point F, just ahead of point F. So now only the vertical component of T will cause a moment, and that will be equal to EF times T cos theta R cos F. It is in the clockwise direction, so I will get minus EF multiplied by T cos theta is equal to 0, and this will give me the answer for M. So this is what we do when we have equilibrium problems of a single body. Now I'll just quickly take a pause for some questions if there are any. Other than that, then I have a couple of more points to cover. I'll talk of something called a two-force member, and I'll talk of multi-member bodies. I'll just introduce them in the class. So let's see. Today's class has virtually been only examples. It was more or less like a tutorial and not a lecture. Are there any questions? No. No queries? Well, I don't know. I was hoping some of you will send me some queries by email. I did not get them. If you have any doubts, again, I will repeat my email address. So far, I have not received any query from anyone. If you want to ask, you can probably get in touch with me. Okay. Now, what we will see in our next class is when we have multiple if there are more than one bodies which are connected and which are in a state of equilibrium. Then how do we solve this? But there is, when we analyze multiply connected bodies, there's one concept which comes in quite handy. Which makes life very easy. And this is the concept of what we call as a two-force member. A two-force member is a body on which external forces act at only 2 points. Only on 2 points external forces act, and this is very important, there are no couples or no moments which act on the body. That is what we call as a two-force member. What is so great about it, we will see. Before that, let us see some examples of two-force members. Let us say I have this link AB on which I have force P1, I have force P2. It is connected on rollers like this. It is connected by a pin. Now clearly, if I draw the free body diagram of AB, at A I will get A along this direction perpendicular to the motion. It should be perpendicular to the motion of the rollers. So this force, let me draw it again. The rollers are moving, so we have to go perpendicular to the motion of the roller. The force in that direction is 0. And I think this is possibly, I may have made an error in the last class. So perpendicular to this is this direction. When I draw the free body diagram of AB, I have to show the force along A is only in this perpendicular to the direction of roller. Okay, I'll just come P1, P2. Now AB, I'll just come, is not a two-force member. But suppose if AB is connected to CD and C, so at C what will I have? At C I will have CX and CY. Why do I have this? Because this is a pin, so it cannot provide any moment. So if I draw the free body diagram of AB, at C I will show CX and CY. Okay, but now when I draw the free body diagram of CD, what do I get? I will get, so, and this I will discuss in the next class, and this follows from third law. If CX and CY are acting like this, then let me draw it again. This is CX, this is CY. They act in the equal and opposite direction on CD. And at D, we have DX and DY. Now, if the weight of CD is negligible, then CD is a two-force member. I'll take up the question first, and then I will, if I have time, I will talk about what simplifications come in life because of two-force member. Okay. The question says, in example 3, why we are not considering forces at C. Now, the reason I'm not considering this is a question which comes in this example when I drew the free body diagram. Let me get that free body diagram also. Just a minute. And a good question, and it's good to get doubts cleared like this. Well, I can't find that. Body diagram. Let's see if I can get to the, yeah. So I'll put both of these together. This was the problem, and this is the free body diagram. Now the question is, why don't I consider the forces at C? The problem tells me I have to find the reactions at E. Now, in fact, here I have not even specified whether if C, in fact, if you recall, I said this is one full structure. So I'm not even saying whether it is a full structure. But irrespective of that, when I have to draw, when I include C, when I'm not separating bodies AC and bodies ED, then forces by the pin at C become internal forces. They are not forces which are acting externally on this body A, B, C, D, E, F. My body was A, B, C, D, E, F. Point C is internal to this. So therefore, I will not show the forces at C in this free body diagram. If I cut the body at C, if I separate out, that means if I'm drawing the free body diagram only of AC part, then I have to show the forces at C. But if C is an internal part in a free body diagram, we do not show any internal forces. Only external forces are to be shown. Does that answer my question? Maybe we can go to that college. Maybe you can ask. I can't see the video, but I hope I hear you. Yeah, please. Okay, so the doubt is cleared now. Okay, thanks. Any more question? Yeah, please. I would like to take up more questions. Okay, thank you. Are there more questions? No. So I think the two force member, I still have some time, isn't it? No. 5 minutes more. So let me then get back to the concept of two force member. So suppose we have a two force member. Once again, we recall what is a two force member. Forces are acting only at 2 points. Now, on those 2 points, many forces can act. For example, if I'm talking of point A on the body, so I have a curved shaped body like this, and forces are acting on this only at points A and B. Now on point A, I can have A1, A2, A3, A4. There can be many forces, and similarly on point B also I can have this thing, any number of forces, and no couples. This is very important. If moments are acting on this body, it is not a two force member. Then what happens? See, these forces we can replace by a single force vector A. These are equivalent to A, which is equal to A1 plus A2 plus AN. and these forces are equal to B, which is equal to B1 plus B2 and so on up to plus Bn. That means I can, this is my body, I show A and I show a force B. Okay. Now equations of equilibrium. So the first equation which I get is A plus B is equal to 0. What does that mean? That A is equal to minus B, which means the forces are equal and opposite at the 2 points of application. Now these 2 points need not be at the end. If we have a point in the middle also, where only at that point in the middle and at a second point in the middle, forces are acting. That means what I'm saying is the shape of the body could be anything. This could be point A where there is a single force acting. This could be point B where there is a single force acting. Okay. So I'll come to a question in a minute. So if the first equation of equilibrium tells me A plus B is equal to 0. And the second one, if I take moments about A is equal to 0, that means the force in B must pass through A. Only then the moment about point A is equal to 0. When I take moments about B is equal to 0, this will give me the force A must pass through B. But we know that A and B are parallel. So what it means is that A and B, which are equal and opposite, must pass through the line joining AB. So what this means is that we know the direction of A or B has to be along AB, which tells us that effectively we have only a single unknown, a force A or a force B, which is passing through the line joining AB. And I'll just pictorially show this before I end. So if this was my original body, this was point A, point B, then the effective reaction, we will have a single force A here, and this will be minus A. If this was the case, so we join A and B, and this force has to act along this line. And so therefore, when you have a two force member, the equations of equilibrium of this are automatically implied if we draw a free body diagram showing only a single force with its line of action known to us as the line joining AB. Now, the advantage of a two force member may not come so much in the member itself, but it comes when we draw the free body diagram of the member to which the two force member is connected. Remember, I started with this example of the rod AB, which had many forces acting. Now, when you draw the free body diagram of the rod AB and you come to the point C, and if you realize that CD is a two force member, then in this free body diagram, instead of drawing CX and CY, what you will show will be a single force C acting along CD. So that is how a free body diagram, a two force member. Remove the C. That is how. Okay. So that is how a two force member CD helps you in the free body diagram of AB. I think that's it. Let's see if there's a question. In the last example, why we have taken reactions at point C towards point C and at point D away from D? Well, I could have taken it the other way around also. And I think that is what I did here. When at C, I could have taken them in the other sense also. But once I take them in this sense for point C, when I go to the free body diagram of this body, I have to show them as opposite because of Newton's third law. I will elaborate on this in the next class when I talk of multi-connected bodies. Thank you.